Hi and welcome to the 39th day of Just Start Programming, the Rust programming language. We are almost at the end. We're almost near the finish line, and today we are going to build a multi-threaded web server, which is still part of the book. So I hope reading the Rust code by the end of 39 days would not be as difficult compared to day one where everything looks complex. So let's do this live in one take, no shortcuts and no secrets. So let's just start programming. All right, so here we are. We have reached chapter 21, the final project, building a multi-threaded web server. Exciting. So I think this would represent a real-world example, I hope. So I think by today we'll be able to decipher most of the code here. So join me. We'll make mistakes, definitely, but we'll try to do our best to fix any issues. If we cannot finish this today, we can extend on the following day. And after that, we'll go through the appendix, and that would conclude our series. Hopefully, we could finish everything by day 40. All right, so let's do this. Yeah, so it's been a long journey. Yes, indeed. But we've reached the end of the book. In this chapter, we will build one more project together to demonstrate some of the concepts we'd covered in the final chapters, as well as recap some earlier lessons. For our final project, we'll make a web server that says hello and looks like figure 21-1 in a web browser. Hello, hi from Rust. Here's our plan for building the web server. First, learn a bit about TCP and HTTP. Listen for TCP connections on a socket. Parse a small number of HTTP requests. Create a proper HTTP response. Improve the throughput of our server with a thread pool. So threading, so it's also quite advanced. Before we get started, we should mention two details. First, the method we'll use won't be the best way to build a web server with Rust. Community members have published a number of production-ready crates available on crates.io that provide more complete web server and thread pool implementations than we'll build. However, our intention in this chapter is to help you learn, not to take the easy route. Because Rust is a systems programming language, we can choose the level of abstraction we want to work with and go to a lower level than is possible or practical in other languages. Second, we will not be using async and await here. Building a thread pool is a big enough challenge on its own without adding in building an async runtime. However, we will note how async and await might be applicable to some of the same problems we will see in this chapter. Ultimately, as we note back in chapter 17, many async runtimes use thread pools for managing their work. We'll therefore write the basic HTTP server and thread pool manually so you can learn the general ideas and techniques behind the crates you might use in the future. Building a single-threaded web server. We'll start by getting a single-threaded web server working. Before we begin, let's look at a quick overview of the protocols involved in building a web server. The details of these protocols are beyond the scope of this book, but a brief overview will give you the information you need. The two main protocols involved in web servers are Hypertext Transfer Protocol, HTTP, and Transmission Control Protocol, TCP. Both protocols are request-response protocols, meaning a client initiates requests and server listens to the requests and provides a response to the client. The contents of those requests and responses are defined by the protocols. TCP is the lower level protocol that describes the details how information gets from one server to another, but doesn't specify what the information is. HTTP builds on top of TCP by defining the contents of the requests and responses. It's technically possible to use HTTP with other protocols, but in vast majority of cases, HTTP sends its data over TCP. We'll work with the raw bytes of TCP and HTTP requests and responses. Listening to the TCP connection. Our web server needs to listen to a TCP connection. So that's the first part we'll work on. The standard library offers a stdnet module that lets us do this. Let's make a new project in the usual fashion. Okay, so cargo new hello. Okay, maybe we can close this one as well. We don't need that anymore. And here, let's come out from here. Let's check if we have hello. No, we only have hello world, hello async, and hello macro. Okay, great. So we can create a cargo new hello. Okay, hello and code dot. Copilot, we can close that. This one as well. What is this? Something is here. Okay, so it compiles. Now enter the code in listing 21-1 in source main rs to start. This code will listen at the local address 127.0.0.1 7878 for incoming TCP streams. When it gets an incoming stream, it will print connection established. Okay, stdnet TCP listener. So let's copy this. stdnet networking primitives for TCP UDP connection. And we have TCP listener, that TCP socket server. Okay, so here we have TCP listener bind to this address. Yep, so error handling here, unwrap, and then listener. Okay, for stream in listener incoming, stream unwrap. Let stream connection established. Okay, let's try this one. Let's run it. Did it run? Yeah, building. Is it still building? Let's try to open it up here. So it's address. Copy. Maybe let me move it here. HTTP can't be reached. It can't be reached. Why? What is wrong? Oh, connection established. Okay. Okay. Okay, so connection established. So it works. You can stop this one also. See. Yep. Using TCP listener, you can listen for TCP connections at the address. In the address, the section before the colon is an IP address representing your computer. This is the same on every computer and doesn't represent the author's computer specifically. And 7878 is the port. We've chosen this port for two reasons. HTTP isn't normally accepted on this port, so our server is unlikely to conflict with any other web server you might have running on your machine. And 7878 is Rust type on a telephone. 7878 is Rust typed on a telephone. 78 RUST. Oh, that's interesting. Phone dial. Let's see. 78. Okay, RUST. Oh, that's correct. RUST. The bind function in this scenario works like the new function in that it will return a new TCP listener instance. It will return a new TCP listener instance. The function is called bind because in networking, connecting to a port to listen to is known as binding to a port. The bind function returns result, which indicates that it's possible for binding to fail. For example, connecting to port 80 requires administrator privileges. Non-administrators can listen only on ports higher than 1023. So if we try to connect to port 80 without being an administrator, binding wouldn't work. Binding also wouldn't work, for example, if we ran two instances of our program and so had two programs listening to the same port. Because we're writing a basic server just for learning purposes, we won't worry about handling these kinds of errors. Instead, we use unwrap to stop the program if error happens. The incoming method on TCP listener returns an iterator that gives us a sequence of streams, more specifically streams of type TCP stream. TCP stream. Does it say? Okay, result TCP stream. Okay. A single stream represents an open connection between the client and the server. Connection is the name for the full request and response process in which a client connects to the server. The server generates a response and then the server closes the connection. As such, we will read from the TCP stream to see what the client sent and then write a response to the stream to send data back to the client. Overall, for this for loop will process each connection in turn and produce a series of streams for us to handle. For now, handling of the stream consists of calling unwrap to terminate our program if the stream has any errors. If there aren't any errors, the program prints a message. We'll add more functionality for the success case in the next listing. The reason we might receive errors from the incoming method when client connects to the server is that we're not actually iterating over connections. Instead, we are iterating over connection attempts. The connection might not be successful for a number of reasons, many of them operating system specific. For example, many operating systems have a limit to the number of simultaneous open connections they can support. New connection attempts beyond that number will produce an error until some of the open connections are closed. Let's try running this code. Invoke code. It doesn't look like a macro, is it? Okay. Invoke cargo run in the terminal, then load this one in the web browser. The browser should show any error message like connection reset, because the server isn't currently sending back any data. But when you look at your terminal, you should see several messages that were printed when the browser connected to the server. Yeah, so we saw this earlier. Sometimes you will see multiple messages printed for one browser request. The reason might be that the browser is making a request for all the page as well as requests for other resources like the favicon .ico icon that appears in the browser tab. It could also be that the browser is trying to connect to the server multiple times because the server isn't responding with any data. When stream goes out of scope and is dropped at the end of the loop, the connection is closed as part of the drop implementation. Browsers sometimes deal with closed connections by retrying because the problem might be temporary. Browsers also sometimes open multiple connections to the server without sending any request, so that if they do later send requests, they can happen faster. When this happens, our server will see each connection regardless of whether there are any requests over that connection. Many versions of Chrome-based browsers do this. For example, you can disable that optimization by using equal private browsing mode or use a different browser optimization. Where is this? By using equal private browsing mode. It didn't say how to do that. The important factor is that we have successfully gotten a handle to a TCP connection. Remember to stop the program by pressing Ctrl+C when you are done running a particular version of the code. Then restart the program by invoking the cargo run command after you have made each set of code changes to make sure you're running the newest code. Okay, so before we continue, I wanted to try something. Run it here. connection established. And then what about I do a car go run? Okay, so it panicked because of unwrap. Yeah, here's the error, address in use, because we're already using it. Then over here, connection is still established for this one. Okay, Control C. Reading the request. Let's implement the functionality to read the request from the browser. To separate the concerns of first getting a connection and then taking some action with the connection, we'll start a new function for processing connections. In this new handle connection function, we'll read data from the TCP stream and print it so we can see the data being sent to the browser. Change the code to look like listing 21-2. Okay, so main is here, no changes to main, it still looks the same. Okay, but now we have handle connection, so let's okay, so it will complain, meaning we need to add in TCP stream here. TCP stream, and then buff reader. Where can we find buff reader? Buff reader is IO. Buff reader. And then lines. Struct buff reader. Maybe we got the wrong. Oh, it's correct. So what is the issue? Quick fix. Buff read. Okay. Buff reader, buff read. Oh, buff read is not here, but we have prelude. Maybe there's some explanation. Okay. We bring stdio prelude and stdio buff reader into scope to get access to traits and types that let us read and write to the stream. Prelude of IO. Okay. CDIO prelude. Prelude. Why is this pipe reader? Prelude. Stories. Prelude asterisk. Okay. So you can do it this way, or yeah, you can also do it like this. In the for loop, in the main function, instead of printing a message that says we made a connection, We now call the handle connection function and pass the stream to it. Handle connection, okay. Handle connection. So instead of printing it, we will call handle connection then stream. Oops. Okay. Stream. So it's not reference. The buff reader adds buffering by managing calls to the stdio read trait methods for us. We create a variable named HTTP request to collect the lines of the request the browser sends to our server. We indicate that we want to collect these lines in a vector by adding vect underscore type annotation. Where is that? TCP. Okay, so from stream, we are creating a buff reader, and then buff reader lines map take while collect. So this one it's a vector here, HTTP request. And then we are printing the HTTP request. Okay. Buff reader implements the buff read trait, which provides lines method. Okay, lines method from buff read trait. So you have this method, lines. Returns the iterator, result string, and error by splitting the stream of data whenever it sees a new line byte. Okay, so splits it according to line by line. To get each string, we map unwrap each result. The result might be an error if the data is invalid UTF-8, or if there was a problem reading from the stream. Again, a production program should handle these errors more gracefully. But we're choosing to stop the program in the error case for simplicity. So unwrap will panic. The browser signals the end of the HTTP request by sending 2 new line characters in a row. So to get one request from the stream, we take lines until we get a line that is the empty string. Once we've collected the lines into the vector, we're printing them out using pretty debugged formatting so we can take a look at the instructions the web browser is sending up to our server. Let's try this code. Start a program and make a request in the web browser again. Note that we'll still get an error page in the browser. The program's output in the terminal will now look similar to this. Okay, so let's try running this. Then from here, we refresh. And we're seeing something. Request handle connection. So it will print this one, this one, this one. Okay, so that worked. Depending on your browser, you might get slightly different output. Now that we're printing the request data, we can see why we get multiple connections from one browser request by looking at the path after get. This first line of request. If the repeated connections are all requesting slash, you know the browser is trying to fetch slash repeatedly because it's not getting a response from the program. Let's break down this request data to understand what the browser is asking for a program. A closer look at an HTTP request. HTTP is a text-based protocol, and a request takes this format: method request, headers, message body. The first line is the request line that holds information about what the client is requesting. The first part of the request line indicates the method being used. Get or post, which describes how the client is making this request. Our client used a GET request, which means it is asking for information. The next part of the request line is slash, which indicates the Uniform Resource Identifier, or URI, the client is requesting. A URI is almost but not quite the same as a Uniform Resource Locator, URL. The difference between URIs and URLs is important for purposes in this chapter, but the HTTP spec uses the term URI, so we can just mentally substitute URL for URI here. The last part of the HTTP version the client uses, and then the request line ends in a CRLF sequence. CRLF stands for carriage, return, and line feed, which are terms from the typewriter days. The CRLF sequence can be written as /r/n, where /r is a carriage return, /n is a line feed. The CRLF sequence separates the request line from the rest of the request body data. Note that when the CRLF is printed, we see a new line start rather than /r/n. Looking at the request line we received from running our program so far, we see that get is the method, slash is the request URI, and HTTP 1.1 is the version. Okay, so that's the first line. Get / HTTP 1.1. After the request line, the remaining lines starting from host onwards are headers. Get request, no body. Try making a request from a different browser asking for a different address, such as /test, to see how the request data changes. Now we know that the browser is asking for, let's send back some data. So we can just do it from here, /test. And let's check again. What is the last printout? Okay, so you see get /test HTTP 1. Writing a response. We're going to implement sending data in response to a client request. Responses have the following format. The first line is a status line that contains the HTTP version used in the response, a numeric status code that summarizes the result of the request, and a reason phrase that provides a text description of the status code. After the CRLF sequence are any headers. After the CRLF sequence are any headers, another CRLF sequence, and the body of the response. Here's an example response that uses HTTP version 1.1 and has a status code of 200, an OK reason phrase, no headers, and no body. Okay. The status code 200 is the standard success response. The text is a tiny successful HTTP response. Let's write this to the stream as our response to the successful request. From the handle connection function, remove the print line that was printing the request data and replace it with the code in 21-3. Okay, so here, this is the response according to a specification. Let's terminate this for now. Handle connection, we'll put the response here. Then stream. Okay, so stream, this stream. Stream, write all response bytes and wrap. And comment this out. Stream, write all. Attempts to write an entire buffer into this writer. Response as bytes. Okay, so this one. Then unwrap. There's an error. Okay, the first new line defines the response. This one. Variable that holds the success message data. Then we call as bytes in our response to convert the string data to bytes. The write all method on stream takes reference to U8 and sends those bytes directly down the connection. Because the write all operation could fail, we use unwrap on any error result as before. Again, in real application, you would add error handling here. With these changes, let's run our code and make a request. We're no longer printing any data to the terminal, so we won't see any output other than the output from cargo. When you load 127.0.0.1 7878 in a browser, you should get a blank page instead of an error. You've just hand-coded receiving an HTTP request, sending response. Okay, so let's run this. Then here we can just remove test. Okay, so it's blank. What happens here? Okay, there's no output, but here maybe we can do a more tools and developer tools. Then we here, bring this down, check on network, do it again. So here we have a response. Response header. Raw request header. Okay, so 200 OK. Okay, so now returning a real HTML. Let's implement the functionality for returning more than a blank page. Create a new file, hello HTML, in the root of your project directory, not in the source directory. You can input any HTML you want. Okay, so this and then it says root directory, maybe at this level, hello. Hello.html. Okay, maybe we can move it somewhere here. Copy this. Hello from Rust. save that. I think we can preview this also. Can we do it from here? Explorer view. No. Review this. I don't know how to preview this. Okay, this is a minimal HTML5 document with a heading and some text. To return this from the server when request is received, we'll modify handle connection as shown in 21-5 to read HTML file and add it to the response as a body and send it. So, okay, status line, response, hello HTML is here. Okay. I think we can copy this part. No other changes from here. Oh, we need to include fs. Our response as bytes, not unwrap. So we'll just comment this out. So fs, quick fix, port fs. There. Okay, and then okay, we run it first. Run it. And from here, do it again. Oh, hello from Rust. There you go. There's a response. Yes, we have a response. Okay, we've added fs to use statement to bring the standard libraries file system. Okay, fs file system module into scope. The code for reading the contents of a file into a string should look familiar. We used it when we read contents of a file for IO project in this thing 12-4. I think this is the mini graph, if I'm not wrong. 12. Yes, right. Next, we use format. Okay, so format is a macro. Where is the format? Format status line here, then contents goes here, then length goes here. Content. Okay, so this one seems like the header part. Then you have the body. Is that correct? HTTP headers and body. Yeah, so it's correct. Okay. Content length. To ensure valid HTTP response, we added content length header, which is set to the size of our response body. Size of our response body, how is it computed? Contents length. Okay, from here. Run this code, cargo, run, and load in your browser. You should see your HTML rendered. Yes. Currently, we're ignoring the request data in HTTP request and just sending back the contents of HTML file unconditionally. That means if you try requesting something else in your browser, you'll still get back the same HTML response. At the moment, our server is very limited to and does not do what most web servers do. We want to customize or response depending on the request, and only send back the HTML file for a well form request to slash. Yeah, so something else, or it could be test also, doesn't matter. It will return hello hi from Rust. Okay, validating the request and selectively responding. Right now, our web server will return the HTML in the file no matter what the client requested. Let's add functionality to check that the browser is requesting slash before returning the HTML file, and return an error if the browser requests anything else. For this, we need to modify the handle connections as shown in 21-6. This new code checks the content of the request received against what we know as request for slash looks like, and adds if and else block treats request differently. So it's being handled like this. If request line is this, then we return this exactly the same thing, else other request. Okay, so we can copy this one. Cancel. Then here, insert it here. Close it like this. Then we indent it. And where do we put else? Else is here. Oh, does it do the we can use to do also. Request line. Where is request line? Request line equals to get handle connection. Buffer reader, so request line, we copy this. Request line buffer read lines next. Okay, so this HTTP request can comment out. Can put this here. Okay. Some other request. Okay, so maybe okay, so let's try running this, and then let's see it for ourselves. If we're going through the explanation, then here instead of test, of course, we'll just leave it as slash. Okay, register an error, empty response. Panicked. I did it panic. What's the issue? Is it supposed to panic? Okay, so this one did not panic. Mhm. Okay, so run this code, you should get HTML in hello.html. If you make any other request, like something else, you'll get a connection error. Let's see, that one is still running. Something else. Okay, so the HTML was not returned. Okay, now let's add the code in 21-7 to the else block to return a response with the status code 404, which signals that the content of the request was not found. It also returns some HTML for a page to render in the browser, indicating the response to the end user. Okay, so here, status line contains 404 HTML, and unwrap contents. Okay, so let's copy this. Goes in the else block. Okay, so but we don't have 404, so create a 404. Maybe here. Uh, not found. Something like that. Let's come back to this one. Yeah, so it will return 404 not found, and then it will display 404.html response. So this is the formatting, and write all responses bytes. Okay, so let's run this. From here, something else. There, not found. Something else, not found. Headers, not found. But if you remove this, hi from Rust, it worked. Okay. Oh, 404 HTML is here. Okay, so yeah, we can copy this as well. 404. And then let's run this again. Here, something else. Yeah. And then if we remove that, like from Rust. Okay, cool. With these changes, run your server again. Requesting should return the contents of hello. And any other request like foo should return an error HTML from 404.html. Alright, so a touch of refactoring. At the moment, the if and else blocks have a lot of repetition. You're both reading files and writing the contents of the files to the stream. The only differences are the status line and file name. Let's make the code more concise by pulling out those differences into a separate if and else lines Then we'll assign the values of the status line and the file name to variables. You can then use those variables unconditionally in the code to read the file and write the response. Listing 21-9 shows the resultant code after replacing the large if and else blocks. Okay, so I was saying that so this part of the code and this one there repeating, so to do some refactoring. So from here, what was done here? If request line equals to get, that is this part, HTTP. Okay, so this one looks like a tuple, status line file name. And here you have status line and file name also. And then here, this is where you read file name. So file name is this part and wrap. So it's still the same as this part, read to string. Yeah. And then length, contents length for this, and then response. All right, so that's how it looks. Okay, so we can copy this. Anyway, we understood the implementation. So if there's an if statement here that gets evaluated and returns it into a tuple. This one. Okay, so we can comment this out. Don't need that anymore. From here, we insert this block. Response. Okay, so response is not used. Did we miss anything? Ah, yes, this part. Write all. Write all. There's some. Maybe we can just put it here. Okay, then it should be fine. Let's run this. So we expect the same behavior. Okay, then test maybe. Maybe let's disable the cache just to make sure. That one or this one should work. Okay. Yep. So that worked. Now the if and else blocks only return the appropriate values for the status line and file name in a tuple. We then use this structuring to assign these two values to status line and file name. Status line and file name using a pattern in the let statement as discussed in chapter 19. Let. The previously duplicated code is now outside the if and else blocks and uses the status line and file name variables. This makes it easier to see the difference between the two cases, and it means we have only one place to update the code if we want to change how the file reading and response writing works. The behavior of the code in listing 21-9 will be the same as that in listing 21-7. Awesome. We now have a simple web server in approximately 40 lines of Rust code that responds to one request with a page of content and responds to all other requests with 404 response. Currently, our server runs in a single thread, meaning it can only serve one request at a time. Let's examine how that can be a problem by simulating some slow request. Then we'll fix it so our server can handle multiple requests at once. Can cancel this. Yeah, so far there was no borrowing that happened here. It's quite straightforward response. Yeah, but let's say, for example, let's do a print line response here. 11, will this work? Yeah, so this one will complain. Oh, might be missing a string literal. Oh, okay, so maybe we can do something like this. Oh, it still works. How about this one? Response as bytes. Yeah, let's try to ruin the code a little bit. Put it here. Put it in this scope. It's not necessary, but just to try something. Yeah, for sure this one will complain. It's not in scope. Not in scope. Oops. How about this? Okay, well, what am I trying to do? Never mind. It's quite odd. Odd in the sense that so far, yeah, so we've managed to pull this off without anything to do with borrow checker at all. It just works. After all we've gone through the previous days, which was quite difficult, but finally in this part it was so simple. Okay, let's try the next one and see. All right, so let's move on. Next one, turning our single-threaded server into a multi-threaded server. Okay, so right now the server will process each request in turn, meaning it won't process a second connection until the first is finished processing. If the server received more and more requests, this serial execution would be less and less optimal. If the server receives a request that takes a long time to process, subsequent requests will have to wait until the long request is finished, even if the new request can be processed quickly. You'll need to fix this, but first we'll look at the problem in action. Simulating a slow request in the current server implementation. We look at how slow processing requests can affect other requests made to our current server implementation. Listing 21-10 implements handling a request to /sleep with a simulated slow response that will cause the server to sleep for 5 seconds before responding. Okay, so what else is here? There's this thread and time duration that is added. So thread and time duration. Okay, and then here file name hello, then get sleep. Oh, so this time it's using a match, and then you have this arm to do this, and then this arm to do a sleep. Okay, so a little bit of advance. Let's copy this. We can comment this out, change the logic to this one. And thread, of course, you can just do a quick fix, import thread. Then duration, quick fix for std time duration. Okay, you can see it here, time and duration. So let's run this. Run is at line 6. And from here to that, let me do a sleep. Okay, so sleep. How many milliseconds? 5 seconds. Finish. 5 seconds. Is it true? 5 seconds. Yeah, from 5 seconds. Okay. We switch from if to match. Yes, so that's the match here. Yeah, so aside from this, it will be underscore. So this will be the default arm here if this one doesn't match. 404. That's explanation. Then we got to sleep, so it will sleep for, yeah, when we execute this, it will sleep for 5 seconds. There are multiple techniques we could use to avoid requests backing up behind a slow request, including using async as we did chapter 17. The one we'll implement is so async. We had that in chapter 17, but in this case, as I said earlier, we will implement a thread pool. Okay. Improving throughput with a thread pool. A thread pool is a group of spawned threads. Let me just stop this first. It's a group of spawned threads that are waiting and ready to handle a task. When the program receives a new task, it assigns one of the threads in the pool to the task, and that thread will process the task. The remaining threads in the pool are available to handle any other tasks that come in while the first thread is processing. When the first thread is done processing its task, it's returned to the pool of idle threads, ready to handle a new task. A thread pool allows you to process connections concurrently, increasing the throughput of your server. Okay. We'll limit the number of threads in the pool to a small number to protect us from DOS. Okay, so DOS is denial of service attacks. If we had our program create a new thread for each request as it came in, someone making 10 million requests to our server could create havoc by using up all our server's resources and grinding the processing of requests to a halt. Rather than spawning unlimited threads, then we'll have a fixed number of threads waiting in the pool. Requests that come in are sent to the pool for processing. The pool will maintain a queue of incoming requests. Each of the threads in the pool will pop off a request from this queue. Okay, so now there's a queue. Okay, handle the request and then ask the queue for another request. With this design, we can process up to n number of requests, and then ask the queue for another request. Oh wait, no. With this design, we can process up to n requests concurrently, where n is the number of threads. If each thread is responding to a long-running request, subsequent requests can still back up in the queue. But we've increased the number of long-running requests we can handle before reaching that point. Okay. This technique is just one of many ways to improve the throughput of a web server. Other options you might explore are the fork join model, the single-thread async I/O model, and the multi-threaded async I/O model. If you're interested in this topic, you can read more about other solutions and try to implement them. With a low-level language like Rust, all of these options are possible. Before we begin implementing a thread pool, let's talk about what using the pool should look like. When you're trying to design code, writing the client interface first can help guide your design. Write the API of the code so it's structured in the way you want to call it. Then implement the functionality within that structure rather than implementing the functionality and then designing the public API. Similar to how we use test-driven development in the project in chapter 12, we'll use a compiler-driven development here. We'll write a code that calls the functions we want, and then we'll look at the errors from the compiler to determine what should change next to get the code to work. Before we do that, however, we'll explore the techniques we're not going to use as a starting point. Okay. We'll explore the techniques we're not going to use as a starting point. Okay, so it's just to read this one. Okay. Spawning a thread for each request. First, let's explore how our code might look if it did create a new thread for every connection. As mentioned earlier, this isn't our final plan due to the problems with potentially spawning an unlimited number of threads, but it is a starting point to get working multi-threaded server first. Then we'll add a thread pool as an improvement, and contrasting the two solutions will be easier. Listing 21-11 shows the changes to make the main to spawn a new thread to handle each stream within the for loop. Okay, so what's in here? Oh, you have a stream, unwrap, then, okay, so here there's a thread spawn. Okay. Thread spawn handle connection stream. As you learn in chapter 16, thread spawn will create a new thread and then run the code in the closure in the new thread. Yeah, so this part here is the closure. If you run this code and load sleep in your browser, then slash in the two more browser tabs, you indeed see that the request to slash don't have to wait for sleep to finish. However, as we mentioned, this will eventually overwhelm the system because you're making new threads without any limit. Yeah, so every request you have a thread that is being spawned. You may also recall from chapter 17 that this is exactly the kind of situation where async and await really shine. Keep that in mind as you build the thread pool and think about how things would look different or the same with async. Okay, creating a finite number of threads. We want our thread pool to work in a similar, familiar way, so that switching from threads to a thread pool doesn't require large changes. to the code that uses our API. Okay, so listing 21-12 shows the hypothetical interface for a thread pool. Struct we want to use instead of thread spawn. Okay, so assuming we have a thread pool struct with a new, okay, so I think 4 here is the limit, and then pool, so pool execute, then you have a closure, so I think pool will be self-limiting to 4. Okay, we use thread pool new to create a new thread pool with a configurable number of threads. Okay, so this is the configuration. In this case, 4. Then in the for loop, pool execute as a similar interface as thread spawn. And then it takes a closure. The pool should run for each stream. We need to implement pool execute, so it takes closure and gives it to a thread in a pool to run. This code won't yet compile, but we'll try so the compiler can guide us on how to fix it. Okay, so I think it's best if we copy this part. This out, and of course it will not compile. Hypothetically, we will have a thread pool struct. Okay. Building the thread pool using compiler driven development. So changes to main RS, then let's use the compiler errors from cargo check to drive our development. Here's the first error we get. Yeah, so use of undeclared. Great, this error tells us we need a thread pool. From here, we already know. Our thread pool implementation will be independent of the kind of work our web server is doing. So let's switch the hello crate from the binary crate to a library crate to hold our thread pool implementation. After we change to a library crate, we could also use the separate thread pool library for any work we want to do using a thread pool, not just for serving web requests. So create librs that contains the following, which is the simplest definition of a thread pool struct that we can have for now. So here, let's copy this, and then in source, add lib. Okay, so now thread pool. Then new, of course, we haven't implemented new yet. Then edit main RS to bring thread pool into the scope. Okay, so I think we have already done this. Hello. Thread pool. Okay, then new. This error here. This error indicates that the next we need to create an associated function named new for thread pool. We also know that new needs to have one parameter and can accept 4 as an argument and should return a thread pool. Okay, so in lib.rs, we will implement thread pool with this function, the associated function. So we come back here. All right, so it accepts usize, which is size, and then it returns thread pool. Yeah, so it just returns thread pool. Let's come back to main. Okay, so now we need to provide the implementation for execute. So that's the error here. Execute. Um, Creating a finite number of threads that we decided our thread pool should have an interface similar to thread spawn. In addition, we'll implement the execute function, so it takes the closure it's given and gives it to an idle thread in the pool to run. We'll define the execute method on thread pool to take a closure as a parameter. Recall from moving captured values out of the closure and the FN traits in chapter 13 that we can take closures as parameters with 3 different traits, FN, FN-mod, and FN-ones. We need to decide which kind of closure to use here. We know we'll end up doing something similar to the standard library thread spawn implementation. So we can take a look at what bounds the signature of the thread spawn on its parameter. The documentation shows us the following. Okay, so this is for thread spawn. The f-type parameter is the one we're concerned with here, f-type. The t-type parameter is related to the return value, and we're not concerned with that. You can see that spawn uses fn1s as a trait bound on f. This is probably what we want as well, because we'll eventually pass the argument we get in execute to spawn. We can be further confident that fn1s is the trait we want to use, because the thread for running a request will only execute that request closure one time. So that's why we have fn1s, which matches the ones in fn1s. The f-type parameter also has the trait bound send and the lifetime bound static, which are useful in our situation. We need send to transfer the closure from one thread to another, and apostrophe static because we don't know how long the thread will take to execute. Yeah, so apostrophe is the lifetime marker, lifetime bound. Okay. Let's create an execute method on thread pool that will take a generic parameter of type f with its bounds. Okay, so here you have execute f self, and then you have this type where f is fn1s plus send plus static. We still use the parenthesis after fn1s. Oh, why do we need? Okay. After fn1s, because this fn1s represents a closure that takes no parameter and returns a unit type. This one. Just like function definitions, the return type can be omitted from the signature, but even if we have no parameters, we still need the parentheses. Again, this is the simplest implementation of execute method. It does nothing, but we're only trying to make our code compile. Let's check it again. Okay, so we add this one. Execute. No, we don't have execute yet. We come here. This is where we add it. Okay, then here it's able to compile. Okay. Compiles, but note if you try cargo run and make requests in the browser, you see errors in the browser that we saw at the beginning of the chapter. The library isn't calling the closure pass to execute yet. Note, a saying you might hear about languages with strict compilers, such as Haskell and Rust, is if the code compiles, it works. But this saying is not universally true. our project compiles, but it does absolutely nothing. Yeah. If we were building a real complete project, this would be a good time to start writing unit tests to check that the code compiles and has the behavior we want. Consider what would be different here if we were going to execute a feature instead of a closure. Validating the number of threads in new. Wait. Consider what would be different here if we were going to execute a feature instead of a closure. Okay, so it means we need to reflect and think about it, how it would look like if we use feature. Anyway, let's continue with this. Validating the number of threads in new. We aren't doing anything with the parameters to new and execute. Let's implement the bodies of this function with the behavior we want. To start, let's think about new. Earlier, we chose an unsigned type for the size parameter because a pool with a negative number of threads makes no sense. Unsigned type. So it should be assigned. However, a pool with 0 threads also makes no sense, yet 0 is perfectly valid usize. We'll add a code to check that size is greater than 0 before we return a thread pool instance and have a program panic if it receives a 0 by using the assert macro shown in 21-13. Okay, so let's stop here for now and continue again on the next day. Hopefully tomorrow if I have the time. Yeah, so we're almost there, almost done. We'll come back here and then let's see how is this, how much more we need to do. Okay, and then here graceful shutdown. Yeah, hopefully for another day 40. So it seems like we're going to end on the 40th day. Alright, so before I finally end, let's just set it over here. Where was that? Pull, yeah, here. Okay. Thank you so much for accompanying me. I hope you learned something as well. And hope to see you the next day. First, let me thank my supporters.